Assalamu alaikum. Today, inshallah, we'll do our lesson on probability. Very attached to our last lesson on combinatorics. So here's our table of contents. We're going to do an introduction, the law of probability, a few events. We're going to do AND events and OR events. So an example of an AND event is what is the probability that you get an even number on a dice and flip a coin and get a heads. That's two AND events. And then the equivalent question, but with an OR statement, would be, what's the probability that you roll a dice and it comes out as an even number, or you flip a coin and get a heads? So not each one of them has to happen, just one of the two, and neither one of those is too bad. Then we'll talk about the 1 minus x trick. The 1 minus x trick is, this is the probability of success, and in order to find the probability of success, maybe you flip it. So you say probability of success is equal to 1 minus the probability of failure. So maybe it's a lot easier to calculate the probability of failure than it is to calculate the probability of success. So this whole thing is the probability of success. Maybe it's better if I kind of put here probability of success, and this x is the probability of failure. So the question might have me say, what's the probability that I get an A on the exam? So probability A on the exam, and it gives me some sort of way that I guess on different answers and all that stuff. Instead of saying that, I'll say 1 minus the probability that I don't get an A, and this is equal to the probability that I get an A on the exam. 1 minus the probability that I don't get an A on the exam. So we'll take a look at that. Then dependent events. Dependent events is when the probability is changing with every single event. So that example could be maybe picking balls out of a box. If every single time I pick out a ball from the box, there's less balls in the box for the next pick. So these are dependent events. When I was talking about here and in OR statements, I was talking about a dice and I was talking about a coin. The outcome on the dice doesn't affect the coin, and the outcome on the coin doesn't affect the dice. So we could call these independent events. And we'll say that for these dependent events, again, we can have AND statements and we can have OR statements. We're usually going to see AND statements. Oops, sorry about that. Okay, so let's take a look. Get the camera, stop shaking. So the probability, the number of successful outcomes divided by the total number of outcomes. This is the general formula for probability. The example is, what is the probability of an even outcome on a dice? So the outcomes on a dice are 1 through 6. And which one of these are even? So it's just 2, 4, and 6. So the number of successful outcomes are 3, 2, 4, and 6. The number of total outcomes are 6, 1, 2, 3, 4, 5, and 6. So the probability of even, 3 over 6, or 1/2. And this is the general topic we're going to use for this vanilla flavor simple probability, is identify how many of the options, these are all the options, how many of the options are we counting as successes? We're counting 2, 4, and 6 as successes. How many total outcomes are there? And then we divide them. So what is this assuming? This is assuming all are equally likely. And you'll see that a lot on the GRE, equally likely. But we could imagine a question where it says, oh, this is actually a trick dice, where it's much more likely to favor a certain number. Maybe it's much more likely to favor the number 6. So this would be a cheat dice. In which case we wouldn't just do the number of successes, 2, 4, and 6, divided by the total number of outcomes. We'd have to take into account that this is a cheat dice that gets 6 more often than usual. If someone asked us, what is the probability of rolling a 6 on the dice, we'd say, well, how many successes are there? There's only one successful option. That's 6. So that'll be my numerator. How many total options there are? There's 6 total options. So that's the probability, 1/6. 1/6 is about 18%. Now if he says, well, this is a trick dice, and it's a trick dice in a way that it lands on 6 twice as likely as it's supposed to. It's only supposed to land on 6 1 out of 6 times, but because it's weighted in a certain way, it actually lands on 6 twice as likely as it's supposed to. So what's the probability then? So I would say the probability of 6 with a little star as a trick dice is equal to the normal probability of landing on 6, which is 1/6, times 2. It's twice as likely because it's weighted. So I would say that's 1/3, or 2 over 6. 2 over 6, which is 1/3. So just keep in mind that for the vast majority of problems, it's going to be this equally likely. 1 through 6, it's a fair dice. But you might receive some sort of problem where things aren't equally likely. And we'll see a few of those too. And if we don't have any of them, maybe I'll make one up. I'm not sure it's in there right now. Okay, if a fair coin is tossed 3 times, what is the probability that it will turn up heads exactly twice? So go ahead and take a second to solve this problem. Okay, well the first thing we need to do is check out the options. Like on the top here, we said, oh, these are all the options. So I went ahead and made a tree of the options. We have 3 flips. So the first flip, HT, and then it branches off HT again, and then it branches off HT again. So the H's are heads, and the T's are tails, and at the end, you get all of these options. So the first option is HHH, 3 heads in a row, heads, heads, tails, head, tails, heads, heads, tails, 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 heads, heads, tails, head, tails, 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 heads. The last one, all tails. So I did this through a tree, but you don't have to do it. You don't have to do it through a tree. If you want to make sure that you got the number right, you say, well, this is kind of like a permutation question from combinatorics. You say, I have 2 choices for the first coin flip. It can either be heads or tails. I have 2 choices for the second coin flip. It can either be heads or tails. And then 2 choices for the third coin flip. So total I have 8 choices. And if I count my outcomes, 1, 2, 3, 4, 5, 6, 7, 8, it works out. So my probability of exactly 2 heads, I think that was the question. Let me double check. Fair coin is tossed 3 times. What is the probability that will turn up heads exactly twice? Very good. So the probability of exactly 2 heads is going to equal the number of successful outcomes divided by the total. Well, I've already figured out that the total is 8. So that's pretty good. Total is 8. Now the question is, how many are successful outcomes? So a successful outcome is defined as exactly 2 heads. Well, this one has 3 heads. That's going to be an X. I want it to be exactly 2 heads. So this one has 2. That's good. This one has 2. That's good. This one has 1. That's a fail. This one has 2. This one has 1. This one has 1. And this one has 0 heads. So I also got 1, 2, 3. So my answer to this question would be 3 out of 8. That's 3 out of 8 is 37.5%. Whatever the answer choices are, if it's a fractions, 3 out of 8. If it's percentages, 37.5. So simple enough. This is sometimes called the sample size, or the sample. And the sample size would be 8. So the sample of possible outcomes are these. The sample size, there's 8 of them. How many of them are successes? 3. Not too bad. And there's really no easier way to solve this question than writing out all the options. Okay, well, let's take a look at the laws of probability. So one of the first laws of probability is that all the probabilities add up to 1. So if I'm doing a dice, there's 6 outcomes in a dice. We already listed them, 1 through 6. And because I say there's 6 outcomes, if I add together the probability of all possible outcomes, it should equal to 100%. Well, 100% is just 1. Not too bad. The other law of probability that's important is that there's no negative probabilities. The lowest probability is 0. So an event is impossible, then we say that the probability of an impossible event is equal to 0. So the probability that a dice comes out at 7 would be 0. 7 is not on a typical dice. It's 1 through 6. So not too bad. We're going to use these. This one sometimes comes up just in the question. It'll ask something like, what you roll 2 dice? What's the probability that they add up to 15? So the probability that you roll 2 dice and sum is 15. And maybe you start to do all this math and you kind of investigate and all these things, but then you step back and say, well, the first dice, the highest number it can come out to be is 6. And the second number, the highest it can come out to be is 6. So it's like you're playing Monopoly with 2 dice. The highest number you can get in 2 rolls is 12. So 15 is the probability of impossible. Impossibility of an impossible outcome, which is 0. The first law, that the sum of all the possible outcomes add up to 1, it's really important sometimes for making questions a little bit easier. We'll see the 1 minus x trick that we talked about, 1 minus the failure equals the success. That only works because all of the probabilities add up to 1. So I can go back one slide. So all the probabilities add up to 1. So 1 through 6 all add up to 1. But I can also say this: probability of success plus the probability of failure equals 1. Why is that? That's the case because you're either successful or it's a failure. There's no third option. So for success plus failure, it encompasses all the outcomes. So all the outcomes can either be categorized under successes or under failures. So probability of success plus probability of failure is the same thing as saying the probability of any outcome. It encompasses all the outcomes. So then I say, well, let's prove the previous formula we're going to talk about. Probability of success equals, well, I have plus failure, so instead I'm going to do minus failure on this side, minus probability of failure on that side. Well, these are going to cancel out. So I get probability of success equals 1 minus the probability of failure. And that's the formula we'll talk about in a few sections. So this probabilities add up to 1. It could come up in a question explicitly, but we use it most commonly for these flipping the question. And we'll see a few examples of that. Okay, so let's go ahead and talk about AND events. So sometimes you're not talking about a single event, you're talking about multiple events, and they're connected by AND. And the rule of thumb is if two events are connected by AND, you multiply the probabilities. So Ahmed rolls a dice and then flips a coin. What is the probability of an even dice roll and a head on the coin? So as soon as I see the word AND, I know it's going to be a multiplication. So I say probability of even times the probability of heads. The probability of even, we've talked about that, 3 over 6. The probability of heads on a coin is 1 over 2. Notice these events are independent. My coin flip and my dice roll don't affect each other. 3 over 6 is the same thing as 1/2. So 1/2 times 1/2, 1 over 4. Not too bad, right? Okay, go ahead and take a second. Try to solve this one. Okay, what is the probability that a fair coin flipped twice will land on heads both times? So this is two events. It doesn't say "and" inside the sentence, but what's meant here is probabilities heads on the first and probability heads on the second. So you might have to read between the lines on these questions. So the probability of heads on the first, well, that's pretty simple, it's just 1/2. Probability of heads on the second is 1/2. Because it's an AND problem, I'm going to use multiplication, and I come out with 1 over 4. Not too bad. Okay, so now it's time to talk about the OR sentences, and the OR sentences are actually some of the more difficult problems that you'll see on the exam, but it's not too bad. The thing that needs to be memorized, maybe I'll just write it right here on the top. This is kind of maybe the cheat. P, A, or B. So A is an event and B is an event. It will always equal the probability that A happens plus the probability that B happens minus the probability of A and B. And as you can imagine, the difficult part of this formula is this part right here, this last term, A and B. And we just learned how to do A and B. So A and B, how do we really do this? It's almost always just multiply. But the problem is kind of realizing when you need to subtract off this A and B and when it's not necessary. And if you subtract it off when you don't need to subtract it off, you get the wrong answer, and vice versa. If you needed to subtract it off and you didn't subtract it off. So the question here is, can A and B happen together? So if you were drawing like a Venn diagram, you'd say here you have the event A, and here you have the event B. So if you want A or B, you say, well, what's A or B? Let's maybe start with that. A or B, as you can just tell from maybe grammar, means either A needs to happen, either A or B, or both. So in mathematics, when we say A or B, we mean either A can happen or B can happen or they both can happen. We have no problem with them both happening. So what is this formula doing? It says first the probability of A. So you shade all of A. And it says, oh, plus add to that the probability of B. So then you shade all of B. And you say, well, then you're done. You say, well, wait a second, there's a problem. This middle spot right here, I counted it when I was doing probability of A, and I counted it when I was doing the probability of B, so it actually got counted twice. When we do mathematics, we don't like it when things get, especially probability, we don't like it when things get counted twice. We want everything to be counted exactly once. So if something is counted twice, and we want it to be counted once, what's the last step? The last step would be to subtract off, maybe I can draw it, this little middle section that was counted twice. It was counted once in probability of B, and it was counted once in probability of A. So it was counted twice, and if we subtract it off once, now it's counted once, which is what we wanted. So that's why you're going to do that. So when are you going to have to subtract off the probability of A and B? You're going to have to subtract them off when the two events, A and B, can happen at the same time. And if they can't happen at the same time, then don't subtract them off. So let's look at an example. Ahmed rolls a dice and then flips a coin. What is the probability that of an even dice roll, and a head? So this is A, and this is B. So the probability of two OR events, meaning the probability of even or head. So I either want an even, or I want a head, or both can happen, no problem. Now the question is, can both happen? I say, yeah, sure. Like an example of them both happening is the dice comes up 2, and then the coin comes up heads. Well, there it is. They both happened. So I definitely should be subtracting off this even and heads. Well, lucky for us, we just solved the question, even and heads, 10 seconds ago. What did we solve? We said even and heads. We said the probability of even was 1/2. The probability of heads is 1/2. Even and heads, as we said here, multiply, is 1/4. The probability of even is 3/6. There's 3 even numbers of the dice, 2, 4, and 6. And there's 6 numbers total. Plus the probability of heads. The probability of heads for flipping the coin is 1/2. Then we always subtract, right? Subtract 1/4, or subtract 1/2 times 1/2. So we get 3/6 is 1/2. So I get 1/2 plus 1/2 minus 1/4. 1/2 plus 1/2 is 1, minus 1/4 equals 3/4. So why did I subtract off even and heads? Because they can happen at the same time. So let me give you an example of this Venn diagram, but in a sample size. And then I'll give you an example of a case where you wouldn't want to subtract off the AND case, because there is no AND case. It might look like there's an AND case, but there's actually no AND case. So let's take a look at this question. Even dice roll and a head. So let me write down all the possible dice rolls. 1, 2, 3, 4, 5, 6. And I'm going to say we got a head on the coin flip. And then the other possibility is 1, 2, 3, 4, 5, 6. And let's say I got a tail on the coin flip. And I've written out the whole entire sample. These are all the possible outcomes. These are 6 outcomes for the coin, and then a head. 6 outcomes for the dice, then the tails. And we could also do this using combinatorics. How many outcomes do you have for the dice? You have 6. How many outcomes do you have for the coin? 2. 6 times 2 equals 12. If you count these up, they indeed add up to 12. Now the question is saying, I'll write it here on the top, even or heads. So let me first say I'll circle all the evens. So I'll circle 2h, 4h, 6h, 2t, 4t, 6t. So I circled all the evens. So if I say an OR statement, only one of these needs to be true. So I first circled all the evens. Then I circle all the heads. So circle all the heads. Done. So if I just solve this question with my diagram, I'll say probability of even or head is going to equal The total number of outcomes are 12. And how many of them are circled? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them are circled. 9 over 12 is the same thing as 3 over 4. Done. So if the question is small, you might just write out all the combinations, circle all the evens, circle over the heads, count the number of them that have circles, and then you're done. The problem is that's not always the case. Sometimes it's way too big to count out. So you'd have to say probability of even, or to write out, plus the probability of head, minus the probability of even and head, and heads. So I'd say, well, the probability of even, how many did I circle in pink? 1, 2, 3, 4, 5, 6. I circled 6. 6 over 12. Plus, how many did I circle when I was doing the heads? Well, I circled everything in green. I circled 1, 2, 3, 4, 5, 6. Well, I also circled 6. 12 over 6. 6 over 12. Now the problem is, some of them got counted twice, meaning some of them got circled twice. And the ones that got circled twice got counted twice. They got counted in this, and they got counted here. So which ones got circled twice? 2H, he got circled twice. 4H, he got circled twice. And 6H, he got circled twice. So there's 3 of them that got circled twice, so I do minus 3 over 12, the ones that got circled twice. So 6 plus 6 is 12, minus 3 is 9. Keep the bottom of your fraction the same, 9 over 12 equals 3 over 4. So if you have the time and you're really kind of uncomfortable with all questions, maybe you can solve it using the formula, but check it by writing it out. You write out all the possible samples, you circle all the evens, you circle all the heads, and then you say, well, how many of them just have circles? I don't care if they're circled twice or circled 3 times. I just want to count all the ones that have circles, divided by the total. So this is the number with circles divided by the total. And that'll always give you the right answer. And then try this one out. What is the probability that a fair dice rolled once will land on either 4 or 5? Okay, well this one's not too bad. So probability of 4 or 5 is equal to the probability of 4 plus the probability of 5 minus the probability of 4 and 5. Okay, the probability that a dice lands on 4 is 1 over 6. The probability that a dice lands on 5 is 1 over 6. What is the probability that a dice lands at the same time on 4 and 5? Well, that's 0. These things cannot happen at the same time. So what is the probability that a fair dice rolled once will land on 4 or 5? What is the probability that it happens at the same time? 0. So this is a simple question. 1 6 plus 1 6, 2 over 6 equals 1/3. So what we should learn from this question is this AND statement, when you put them both together, you can't just always multiply. You say, well, okay, well, this is an AND statement, and is always multiply 1 6 times 1 6 equals 1 over 36. Subtract that off. You have to also kind of see logically, can these two events happen at the same time? Can we have an even with the heads happening at the same time? Yeah, one of them is happening on the dice, one of them is happening on the coin. I showed that they can happen at the same time. But can we have 4 and 5 landing on a single dice at the same time? Nope, so you don't have to worry about that, and you're just going to do 1 over 6 plus 1 over 6 minus 0. Let's look at another one. If a dice is rolled twice, okay, things are getting interesting. What is the probability that it will land on an even number both times? So, probability that it will land on an even number both times. That sounds to me like an AND question. Probability of even on the first, and the probability of even on the second. Okay, so probability of even on the first, this is a dice, is 1/2. The probability of even on the second, 1/2. Half of the numbers on a dice are even, half of them are odd. It's an AND question. I multiply, I get 1 over 4. No problem. I know that these are kind of tough sometimes, but the homework will clear up if you're not getting too many of these right. Okay, 8 runners in a race are equally likely to win the race. That's important to know. What is the probability that the race will be won by the runner in lane 1 or in lane 8. Go ahead and take a second to try to solve this one. Okay, hope this wasn't too bad. So the probability of lane 1 or lane 8, that's equal to the probability of lane 1 plus the probability of lane 8 minus the probability of lane 1 and lane 8. Well, is it possible that the person in lane 1 and the person in lane 8 both win? That's not possible. There's no ties. 0. So either someone has to win and two people can't win at the same time. So this and term, kind of like the case with the 4 and the 5, it's 0. They can't happen at the same time. You can't get a 4 and a 5 happening at the same time, and you can't have lane 1 and lane 8 both winning at the same time. So all I have to do is do these two. The probability that the person in lane 1 wins is 1 over 8. There's 8 people in the race, and they said they're all equally likely to win. The person that the one in lane 8, that's also 1 over 8. So I get 1 over 8 plus 1 over 8 is 2 over 8, which equals 1 over 4. Not too bad. Okay, let's look at one again, where the AND statement, we need to take into account the AND statement, so go ahead and pause the video. Okay, suppose that a box contains 20 balls, 10 of them are white, and they have the numbers 1 to 10 on them. So I have white 1, white 2, the last ball I have is white 10. And then I have 10 more balls that are red, and they have 11 to 20 on them. So maybe I'll do that in a different color. We have red 11, red 12, the last ball we have is red 20. And what's the question? If one ball is selected, what is the probability that the ball will be white or will be marked with an even number? Okay, so probability white or even is going to be equal to the probability of white, that's all of these balls, plus the probability of even, that's going to be like the 2, the 12, the 10, the 20, all the ones in between that are also even, minus, do this in a different color maybe, the probability that it's white and even. And there are some that are white and even. One of them is right here, W2. One of them is right here, W10. So those definitely exist. Well, the probability of the white, there's 20 balls, 10 of them are white. So the probability of white, other than blue, is 1/2. The probability of even, you can count them out on your fingers, but there's 20 balls. So if there's 20 balls, half of them are odd, half of them are even. It starts at 1 and it ends at 20. You can double check, but you're going to find that half of them are odd and half of them are even. So that's 1/2 also. So probability of even, 1/2. Probability of white is 1/2. So far it adds up to 1. That's not the case. We definitely need to subtract off white and even. Well, how many of them are white and even? Let's go ahead and count them out. The ones that are white and even, I can do that in green. W2, W4, W6, W8, and W10. 1, 2, 3, 4. There's 5 balls that are white and even. So let's use the formula that's on the very first slide of the presentation. The number of successful outcomes, there's 5 of them. 1, 2, 3, 4, 5. 5 successful outcomes divided by the total number of outcomes, or how many balls are there? There's 20. The total number of outcomes are 20. And that's our answer. All we have to do now is do some number crunching. 5 over 20, you can divide the top and the bottom by 5, and you get 1 over 4. 20 divided by 5 is 4. 5 divided by 5 is 1. A half plus a half, we said, was 1. And this sign should be minus. So 1 minus a fourth, well, 1 is 4 over 4. So the answer is 3 over 4. 3 over 4. Okay, hope that wasn't too bad, or too painful. Let's take a look at what's next. A fair die is rolled, and a fair coin is flipped. So fair means equally likely. What is the probability that either the die will come up 2 or 3. So that's an or statement. Or the coin will land heads up. So we have 2 or statements. So go ahead and pause the video and try this one out. If you're getting frustrated, please stick with me, find me on campus. Probability is notoriously tough to kind of grab on your first time, but this is nothing that we can't do. So probability of, I'll say, dice or coin. So probably the dice is successful or the coin is successful. So this is equal to the probability of dice plus the probability of coin minus the probability of dice and coin. Cool, so let's look at the probability of dice. A pair of dice is rolled. What is the probability that it will either come up 2 or come up 3? So I'll just grab a dice real quick. Say these are the options. I want it to be either 2 or 3. So the successes are 2 and 3. The total number of outcomes are 6. So the probability of 2 or 3 is equal to 2 over 6. We can just do that kind of logically, kind of like how we did the probability of evens. We said 2, 4, and 6. Those are the 3 evens, 3 over 6. If you want to do it like very rigorously, you can say, okay, probability of 2 or 3 is equal to the probability of 2 plus the probability of 3 minus the probability of 2 and 3. Well, the probability of 2, 1 over 6. The probability of 3, 1 over 6. The probability that 2 and 3 happen at the same time on a single dice roll, well, that's 0. 1/6 plus 1/6 is 2 6, which is equal to 1/3. So I'm going to go ahead and fill in for probability of dice, 1/3. Now I'm going to do the coin. The coin lands heads. Well, the probability the coin lands heads is 1/2. Now I want the probability of dice and coin. Well, the probability of dice and coin is an and question. So maybe I'll extract it right here and do it in pink. Probability of dice and coin. And I said with the and questions, you just multiply. So probability of dice is 1/3. Probability of coin is 1/2 equals 1 over 6. So probability of dice and coin is 1 over 6. Now you might say, like, well, before I do this step, there should be a small step before that where you say, is it possible? Is this even possible for this to happen? I say, yeah, it is possible. One thing is happening on a dice, one thing is happening on a coin. I can imagine plenty of cases inside this and scenario. One of them is 2 heads. 2 heads is inside the and scenario. 3 heads is inside the and scenario. So the question should be, before you start doing, well, probability of dice and coin is equal to probability of dice times the probability of coin, you should have an intuitive step. The intuitive step is, can these 2 events happen at the same time? In this case, the answer is yes. Dice coming up 2 or 3 and coin coming up heads can happen at the same time. The question here is, can the probability of 2 and the probability of coming up 3 happen at the same time? Sorry about that. Can it happen at the same time on a single dice? And the answer is no. So here is 0. Okay, so 1 over 3 is 2 over 6. 1/2 is 3 over 6. And then minus 1 over 6. Okay, so 2 plus 3 is 5, minus 1 is 4. So it's going to equal 4 over 6. 4 over 6 divided the top and the bottom by 2 equals 2/3. That's your answer. So it wasn't too bad. The classic question of R. We did the probability of dice, the probability of coin, minus the probability of the AND statement. The AND statement was just take the dice and take the coin and multiply them by each other. And before we did that last step, the step in the pink here, we made sure that these 2 events could logically happen at the same time. Okay. Let's move on to the 1 minus x trick. Okay, the 1 minus x trick, sometimes in trying to calculate the probability of success, it's actually easier to do 1 minus the probability of failure. So in that case, we're going to flip the question. We're going to pretend like the question is asking us to calculate the probability of failure. Then we're going to do 1 minus. And we already showed on a previous slide why this works. So let's jump into it. This kind of trick will always save you time, but you can usually do it the regular way and still get the right answer. What is the probability that on 3 rolls of a single fair die, at least one of the rolls will be 6? At least one of the rolls will be 6. This at least one is a classic case of doing this 1 minus the failures trick. So at least one. Well, we have 3 rolls. 3 rolls. So what does that mean? It means you can either have 1 6, so 1 6 can come up, or you can have 2 6s come up, or you can have 3 6s come up. So if you wanted to solve this question directly, you have to find the probability that you have exactly 1 6. That would be this. And then you have to add to that the probability of exactly 2 6s. Then you have to add to that the probability of exactly 3 6s. There's 3 cases where you can satisfy this condition. At least one of the rolls be 6. Now, if we flip the question, well, what's the opposite of this? The opposite of this, the probability of failure, or the failure statement, is no 6s. If I have 1 6, if I have 2 6s, or if I have 3 6s, these are all called success. If I have no 6s, that's called failure. So if I flip the question and make it a question of failure, there's only one case to solve. And once I do that, I'll say in the last step, probability of success is equal to 1 minus the probability of failure. And let's go ahead and do that. So let's first calculate the probability of failure. The probability of failure, you have 3 rolls and you want no 6s. So this is AND. So I want probability of no 6 on the first and no 6 on the second and no 6 on the third. And we said for AND statements, the math is really easy. You always just multiply. So what's the probability that you have no 6 on the first? That's 5 over 6. I can have any of the numbers come up except for 6. I'm okay with 1, 2, 3, 4, 5. And then likewise 5 over 6. And then likewise 5 over 6. So the probability of failure right here is equal to 5 over 6 times 5 over 6 times 5 over 6, or 5 over 6 cubed. And this is 1 minus. And then hopefully that would be the answer on the multiple choice question. It would just be like this. Or maybe they would write it as 5 over 6 to the power 3. If they want you to multiply it out, it's also not a problem. So how would you multiply this out? When you multiply fractions, you multiply all the tops, and then you multiply all the bottoms. I'll do it up here. So you multiply all the tops, you multiply all the bottoms, so you'd go on your calculator on the exam, say 5 times 5 times 5, and if you do that, you get 125. Then you multiply the bottoms, 6 times 6 times 6, and if you do that, you get 216. So it's 1 minus 216 equals the probability of success. Well, 1 is the same thing as 216 over 216. 216 over 216. So I would do 216 minus 125. They have the same denominator, so all I have to do is subtract the tops. And if you do that, you get 91 over 216. And that would be your answer as a fraction. Okay? So that's a question of flipping. Let's look at the next one. If a die is rolled twice, what is the probability that it will land on an even number at least once? Even number at least once. And doing 2 rolls. So we have at least once question. At least once, sorry. And then we have 2 rolls. So the success could be 1 even. 1 even is a success. The other successes are 2 evens. And these are called successes. There's 2 cases of success. Now let's go ahead and try to flip the question and make it a failure question. So that means at least 1. So failure, our articulation of what failure would be 0 even rolls. That'll be our articulation of failure. And there's only one outcome. There's 3 rolls. So if there's 2 rolls, sorry. There's 2 rolls. We're either going to have 0 evens, 1 even, or 2 even. The 1 even and 2 even, those are successes. The 0 even, that's a failure. So if you wanted to solve this question directly, you'd have to calculate 1 even, and you'd have to calculate 2 even, and then you'd have to add those two numbers together, and you'd get the answer. Or we can flip it. So when we flip it, we're going to say the probability of success is equal to 1 minus the probability of failure. The probability of failure means 0 even rolls. So 0 even rolls to me, probability of 0 even means the probability of no even on the first and the probability of no even on the second. Well, what does no even mean? No even just means odd, so I can kind of cross out this silliness and just write odd. Odd. So probability of odd in the first and odd in the second. The probability of rolling a dice and getting an odd is 1/2 or 3/6. This one's also 1/2. And this is an AND statement. AND is just multiply. So the probability of 0 evens on 2 rolls, that's what the question says, is the probability of getting an odd in the first one and an odd in the second one, which is equal to 1/4. And this is the probability of failure. Now we plug that in right here, probability of failure. And we get that the probability of success is equal to 1 minus 1/4 or 3/4. I feel like 3/4 was a very popular answer today. 3/4. Hope that's not too bad. Okay, a few more practice questions. In a box with 10 blocks, 3 of them are red. What is the probability of picking a red block on each of your first 2 tries? Each of your first 2 tries. Assume that you do not replace the first block after you have picked it. So this is our last topic, dependent events. So after I pick the first block, I don't put it back in. So that block doesn't even exist for the next picking. So these are going to be and statements. So I want the probability of getting 2 red. So probability of red on the first pick and the probability of red on the second pick. Cool. So the probability of red on the first pick, well, there's 3 red and there's 10 blocks total, and they're all equally likely. I guess they're all equal in size. So that's 3/10. Now it's and, so I'm going to put a multiply sign. And now I want to get a red on the second pick, but I do not replace it. That means now in the box I don't have 10 blocks anymore. Now I have 9 blocks left in the box. And how many of them are red? Only 2 of them. I already took one of the red blocks out. Now there's only 2 red left. So this is, I guess I'd say the formula is red over total. So my first pick, red over total, is 3/10. But after I've already successfully taken a red, now it's 2/9. It's only 2 red blocks and a total of 9. And that's going to be my answer. So I'm going to multiply the tops and get 6. Multiply the bottoms and get 90. If you want to simplify this fraction, you can divide by 3 on the top and the bottom. Get 2/30. Then you divide by 2 on the top and the bottom, and you get 1/15. So this is dependent choices. When we were doing dices and coins, those two things, they didn't affect each other. The probability of getting heads on the coin was always 1/2. It didn't matter what you got on the dice. Now, as soon as I pick one of the blocks out of the box, that block doesn't exist anymore. So these probabilities, they change. So this is dependent. Dependent. Sounds kind of complicated, but it's not too bad. And these will almost always be and statements. So just break it down, red on the first pick, red on the second pick, and solve each one of these separately, kind of saying to yourself, okay, I've already gotten a red on the first pick. Now what is my new number of red blocks and my new total blocks in the box? So let's go ahead and give you guys a practice question. A drawer has 7 white shirts and 3 red shirts. The zoom isn't quite there. Let me see if I can get it to focus. Oops. Okay, and what is the probability of picking a white shirt followed by a red shirt if the first shirt is not put back in? So the first shirt is not put back in, immediately it's called dependent. Some people, they don't even call it dependent, they call it no replacement. No replacement. Questions of no replacement. That's another way of calling these questions. So I'm going to go ahead and break it down. The probability of white on first, and I want this to happen next, red on second. Probability of red on the second pick. Okay, not too bad. The probability of white on first, well, there's 7 white shirts. And how many shirts are there total? 7 and 3, 10 shirts total. Times, because it's an and statement. And I've already taken 1 short out, so I know there's only 9 shorts left in the drawer. And the question is, how many of them are red? Well, I took out a white one. I didn't even touch the reds, so there's still 3 red shirts. If I wanted to get a white on my second pick, then yeah, I would have to do 6 over 9, because I've already taken 1 of the white shirts out of the drawer. But I haven't done anything to the reds. They started with 3. By the time I'm taking my second picking out of the drawer, there's still 3. So this is going to be 3 over 9. And then 7 times 3 is 21. And 9 times 10 is 90. Divide the top and the bottom by 3. And you get 7 over 30. Okay, I think that's the last one.